There is a material sitting in a lab in Texas right now that, according to the textbook rules of physics, should barely conduct electricity at all. Its electrons are supposed to be almost frozen in place, trapped, going nowhere. And yet, at a cold enough temperature, that same material lets electricity flow through it with zero resistance. Not low resistance, zero. No loss, no heat, no waste. Scientists call this superconductivity, and this particular version of it was not found by a chemist getting lucky in a lab. It was found by artificial intelligence, guided by the strange rules of quantum physics, searching through a space of possibilities too large for any human team to check by hand. And when they found it, some physicists looked at the result and basically said the same thing. This material works, but by the old rules, it really shouldn't. To understand why that is such a big deal, you first need to understand what superconductivity actually is, because it is one of the strangest, most useful phenomena in all of physics. Picture a river. Even the calmest river loses a little energy to friction as the water rubs against the riverbed and the banks. Every wire in your house, every power line running across the country, every charging cable you own works the same way. Electricity flows through metal, and the metal fights back a little, and that fight turns into heat. That is resistance. And it is the reason your phone charger gets warm, the reason power plants lose a chunk of their electricity before it ever reaches your house, and the reason your laptop needs a fan. A superconductor is a material where that friction disappears completely. Zero resistance. Electricity that flows forever in a closed loop without losing a single drop of energy. It sounds like something out of science fiction, but it is real. It has been real since 1911. And it already powers things you have heard of, like the giant magnets inside MRI machines and the particle accelerators used to study the building blocks of matter. Here is the catch, and it is the catch that has frustrated physicists for over a century. The superconductors we already know how to build only work if you cool them down to absurdly low temperatures, often colder than outer space. That means expensive refrigeration, liquid helium, and equipment the size of a room just to keep a wire cold enough to behave. The dream, the one scientists have chased since the 1980s, is a superconductor that works at or near room temperature, something you could use in ordinary power lines and computer chips without needing a walk-in freezer to make it function. If that dream ever becomes real, it could quietly reshape how the entire planet uses electricity. And that dream is exactly what a new discovery in 2026 has pushed a little closer in a way nobody fully expected. The problem with finding new superconductors has never really been a lack of effort. It has been a lack of options that anyone could actually check. Think about how many ways you can combine elements from the periodic table into new compounds. Now think about how many of those combinations might, under the right conditions, become superconductors. The number of possible materials is not in the thousands. It is not even in the millions. It stretches into numbers so large that testing them one at a time in a lab, the old-fashioned way, would take longer than human civilization has existed. For decades, most superconductor discoveries came down to educated guessing, chemical intuition, and a healthy dose of luck, which is exactly the kind of problem artificial intelligence turns out to be very good at solving. But even AI on its own does not know which combinations are actually promising unless it understands the underlying physics. And this is where quantum mechanics had to step in, not as a buzzword, but as the actual rulebook the AI was trained to respect. In 2026, an international research group called the SuperC Consortium, led by physicist Päivi Torma at Finland's Aalto University, tried a different approach to this old problem. Instead of testing materials one at a time, they built a machine learning system that could scan an enormous range of possible compounds and quickly flag the ones most likely to behave like superconductors, based on quantum-level calculations of how their electrons would actually move. Rather than running the full, expensive physics simulations on everything, the AI acted like a filter, narrowing an almost limitless set of candidates down to a short list worth taking seriously. Then, and only then, did the team run the heavier, more precise quantum calculations on that short list. It is a workflow, not a single lucky guess. And what that workflow eventually pointed to was something that made a few physicists pause. Before we get to what they found, you need to understand one more piece of the puzzle, because it is the part that makes this whole story make sense. Some crystal structures in nature are arranged in a pattern called a kagome-lattice, named after a traditional Japanese basket weaving pattern made of interlocking triangles and hexagons. It looks beautiful under a microscope, but it does something strange to the electrons living inside it. In most metals, electrons behave a bit like cars on an open highway, free to speed up, spread out, and carry energy efficiently from one place to another. In a kagome-lattice, the geometry of the triangles causes something called a flat electronic band. In simple terms, the electrons get boxed in. Their paths interfere with each other so precisely that, in theory, they lose almost all their ability to move freely. Imagine a highway, where every lane is suddenly bumper-to-bumper gridlock, permanently, no matter what time of day it is. Physicists have long expected that materials like this should be poor conductors at best, because sluggish, trapped electrons are not supposed to be able to pair up and flow together the way superconductivity requires. There is actually a deeper reason physicists have historically avoided kagome materials in their superconductor hunts, and it is worth pausing on, because it explains why this result raised eyebrows, instead of just getting filed away as one more incremental paper. Superconductivity, in the classic explanation developed back in the 1950s, depends on electrons finding a partner, forming what physicists call a Cooper pair, and then that pair moving through the material together, undisturbed. For that pairing to happen efficiently, electrons generally benefit from having some freedom of movement, some kinetic energy to work with. A flat band strips almost all of that kinetic energy away by design. It is a little like asking two people to dance a fast, coordinated routine while both of their feet are stuck in wet cement. On paper, it should not work well at all. For decades, that expectation quietly steered researchers away from spending time and money testing kagome compounds for superconductivity, because the odds looked bad and lab time is expensive. The AI system built by the Super-C team did not share that assumption, or rather, it was built to check the assumption directly against the underlying quantum geometry instead of relying on decades-old intuition. And that is precisely why it noticed something a human search, guided by old habits, might have skipped past entirely. And that is exactly the rule this new discovery seemed to break. Using their AI-guided screening process, the Super-C team identified two new compounds worth testing closely: yttrium ruthenium boride and lutetium ruthenium boride, known by their chemical shorthand as YRu3B2 and LuRu3B2. Both have that same kagome-lattice structure, the same supposedly gridlocked electrons. The team's collaborators at Rice University in Houston, Texas, synthesized the materials in the lab and tested them directly. And both compounds turned out to be genuine, confirmed superconductors. Electrons that, by the textbook, should have been too trapped to cooperate were somehow pairing up and flowing with zero resistance anyway. The results were published in the peer-reviewed journal Physical Review Research in the summer of 2026, and the reaction inside the field was less about the specific materials and more about what their existence seemed to be quietly proving wrong. Now, before this starts to sound like the room temperature breakthrough everyone has been waiting for, let's be honest about the numbers, because the numbers matter here. These two materials become superconducting at 0, 81 Kelvin, and 0, 95 Kelvin. That is less than 1 degree above absolute zero, colder than deep space, colder than almost anything you will ever encounter. This is not a material you will find in your phone charger or your car battery anytime soon. So why are physicists excited about something that only works a hair above the coldest temperature physically possible? Because the real discovery here was never really about those two specific compounds. It was about proving that flat-band kagome materials, the ones everyone assumed should be bad conductors, can superconduct at all. That single fact reopens an entire category of materials that many researchers had quietly written off. So how does a material with supposedly gridlocked electrons manage to superconduct anyway? This is where the quantum half of the story earns its place in the title, and where the explanation gets genuinely elegant. It turns out that whether electrons can pair up and flow together does not depend only on how fast individual electrons move. It also depends on something called quantum geometry, essentially the shape and structure of the electrons' underlying wave patterns as they exist across the material. Think of it less like a highway full of stalled cars and more like a stadium full of synchronized swimmers. No individual swimmer needs to move fast through the water for the group to create a smooth, coordinated wave across the pool. What matters is how well their movements line up with each other. In a similar way, even electrons trapped in a flat band can still superconduct if their quantum wave patterns are shaped in a way that lets them cooperate. The AI-guided screening the Super-C team used was specifically designed to search for that kind of favorable quantum geometry, not just raw electron speed. That is the piece of physics that let them find superconductors hiding in a category of materials most searches would have skipped over entirely. This was not an isolated result either, and this is where the story gets bigger than one lab in Finland. A few months earlier, in December 2025, researchers at Tohoku University in Japan, working with the technology company Fujitsu, used a different AI system to analyze real experimental data from a separate superconducting material made of vanadium, antimony, and cesium. Their AI was not searching for new compounds. It was trying to figure out the causal relationships behind an already known superconductor's behavior, essentially asking why it works the way it does, not just that it works. And in January 2026, a team at the Hopkins Applied Physics Laboratory in Maryland used their own predictive AI model, trained on real materials data, to identify an entirely new superconducting compound from scratch. 3 separate teams, 3 separate countries, 3 different AI approaches, all converging on the same idea within about 6 months of each other. That is not a coincidence. That is a field shifting. What is interesting about all three of these projects is that none of them used AI the same way. The Tohoku and Fujitsu team used it as an interpreter, feeding it real experimental measurements and asking it to explain the physical cause behind a superconductor's behavior, something researchers can normally spend years untangling by hand. The Johns Hopkins team used it more like a predictor, training a model on known materials data and then asking it to point toward compounds nobody had tried yet. And the Super C team used it as a filter, cutting a nearly infinite list of possibilities down to a manageable handful before spending real computing time and real lab resources on them. 3 different jobs, one shared idea underneath all of them. Let the AI handle the scale of the search, and let human physicists and real experiments handle the confirmation. Nobody in any of these papers is claiming the AI discovered anything on its own without human scientists checking its work in a lab. That distinction matters, and it is one the more careful researchers in this space are quick to point out whenever the coverage starts to run ahead of the actual results. And that brings us to the second half of the title, the part that is easy to get wrong if you are not careful, so let's slow down here. Quantum in this story does not just mean the quantum physics equations used to guide the AI search. There's also a second, more literal meaning creeping into the picture, and it involves actual quantum computers, the experimental machines that use quantum bits instead of ordinary ones and zeros. In March 2026, IBM, working alongside the Department of Energy's Quantum Science Center at Oak Ridge National Laboratory, along with researchers from Purdue, the University of Illinois, Los Alamos, and the University of Tennessee, ran a real quantum computer simulation of a magnetic material and compared the results directly against actual neutron scattering experiments performed at a national laboratory. The simulation matched the real-world data with a level of accuracy that surprised even some of the scientists involved. That result was not about superconductors specifically. It was about proving that today's still imperfect quantum computers can already simulate real quantum materials accurately enough to be scientifically useful, not just theoretically interesting. Here is why that distinction matters, and why we should be precise about it instead of blurring the two stories together for a punchier headline. The Kagome superconductor discovery used quantum mechanics, the equations, run on ordinary supercomputers guided by AI. The IBM and Oak Ridge result used actual quantum computer hardware to simulate a different but related class of material. These are two separate threads of the same larger effort, not one single breakthrough. But they are pulling in the same direction, toward a future where quantum computers themselves might eventually run the simulations that AI currently has to approximate, potentially making the search for new superconductors even faster and more precise. Experts are genuinely divided on how soon that convergence happens. Some researchers think practical quantum computer-assisted materials discovery is still years away. Others believe the pieces are already falling into place faster than expected. Nobody serious is claiming it has fully arrived yet, and you should be skeptical of anyone who tells you otherwise. So why should any of this matter to you, sitting there watching this video on a device that is ironically part of the problem this research is trying to solve? Superconductors are not just a curiosity for physics nerds. Power lines lose a real, measurable percentage of their electricity to resistance every single day across the entire country, every single second. Data centers, the massive buildings full of servers that run the AI systems you use, along with your streaming, your cloud storage, and basically the entire internet, consume enormous and rapidly growing amounts of electricity. And a meaningful chunk of that gets wasted as heat, which is exactly why those buildings need industrial-scale cooling systems just to keep running. A practical, higher-temperature superconductor could cut those losses dramatically, shrink the size of MRI machines in hospitals, make maglev trains cheaper to build, and even make future fusion reactors more efficient. This is not a small, niche corner of physics. It is one of the most economically important open problems in material science, and there is a real chance that AI just handed researchers a faster way to search for the answer. There is also a strange, almost circular part of this story that is worth sitting with for a second. The same AI systems being used to search for better superconductors are themselves part of the reason electricity demand from data centers has climbed so sharply over the past few years. Training and running large AI models takes enormous amounts of power, and a lot of that power gets lost the same way it always has, as heat, through ordinary resistance and ordinary wires and chips. So in a very literal sense, AI is being pointed at the problem of its own energy appetite. If a practical superconductor for computing hardware ever does arrive, it would not just help power grids or hospitals. It could directly reduce the environmental and financial cost of running the very technology that helped find it in the first place. That is not a guaranteed outcome, and nobody involved in this research is promising it will happen on any particular timeline. But it is a genuinely interesting loop to think about. And it is part of why energy researchers, not just physicists, have started paying closer attention to this corner of materials science. That said, let's stay grounded because this field has a history of getting ahead of itself. Room temperature superconductivity has been claimed before, only for some of those claims to later face serious scrutiny or fall apart entirely under closer scientific review. The SuperC Consortium's own stated goal is to reach a room temperature superconductor by 2033, which sounds impressively specific, but it is a target, not a promise, and physicists inside and outside the project openly acknowledge that timeline could easily slip. What actually happened in 2026 was narrower and, honestly, more trustworthy than a room temperature headline would be. Researchers proved that a category of materials long assumed to be poor candidates for superconductivity can, in fact, superconduct. And they proved it using a search method that can now be pointed at millions more candidates, far faster than any human team could manage alone. That is not a finished dream. It is a genuinely new tool for chasing it, tested and confirmed in the real world. Not just a computer simulation left untested on a shelf. If this kind of research is the sort of thing you want to keep following, going deeper into how AI is quietly reshaping physics and material science, hitting subscribe means you won't miss the next one of these stories as it happens. For over 100 years, the search for better superconductors has mostly been a story of patient trial and error, brilliant scientists testing one material after another and hoping the universe would cooperate. What changed in 2026 was not the destination. Room temperature superconductivity is still not here. What changed was the method of the search itself, a rule that most physicists treated as close to settled, that gridlocked flat band electrons make for poor superconducting candidates, just got quietly overturned by a discovery that machines helped surface and humans confirmed with their own hands in a lab. The materials involved are still impractically cold, still years away from anything you will touch or use. But the confidence that a shortcut through the impossibly large space of chemical possibilities actually works, that confidence is not cold at all. It is very real. It is happening right now across labs in Finland, Texas, Maryland, Japan, and Tennessee, and it is worth watching closely because the next material this same method uncovers might not need to be nearly this cold to still be worth writing a headline about. If you want to see where this search goes next, stick around and subscribe because this is a story that is only getting started.